To attend my master's thesis presentation on experimental investigation of flames in complex geometries. So I've cut this presentation into 5 different sections where I'll be taking you through the introduction of what exactly happens in real life scenarios and what are we dealing with as in inhomogeneous Springs flames, and the experimental setup that we had implemented to realize the idea that we had in mind, and then the observations followed by conclusions on these future scores. So running quickly into the introduction. In real-life scenarios, we have combustible mixtures entering in different cases, for instance, in a pipe when we transport methane or natural gas, or for instance, in a ventilated or an unventilated coal mine. So there are possibilities of an ignition when there is a source of ignition, of course, present, and this can actually transform into an explosion further. The case that we're dealing here is with inhomogeneous Springs flames, and as the name suggests, inhomogeneous is unevenly distributed unevenly distributed fuel and air mixture as in real life. And premix flames, as again the name suggests, it's the fuel and oxidizer which is mixed before getting into the combustion chamber. The premix flames are used when we want to have intense combustion in small volumes, and that is the actual idea behind the study. And the objective for this will be to analyze the quantitative and qualitative properties of the inhomogeneous premix flames in complex geometries with obstructors. So the experimental setup was actually a T-section where we
can switch off the lights.
Getting back on this, we have a T-section where this is the section 1 and this is the section 2 and section 3 of the pipe. This pipe is made of polycarbonate material with 600 mm in length for each section, which is equal, it is all equal distance, and then the external diameter for the pipe is 60 millimeters with a pipe thickness of 6 millimeters. The obstacles in this section were semicircles, pretty much half circles of 54 mm diameter, with 60 mm distance between themselves and 3 millimeters thick, and the obstacles are also made from the same material, polycarbonate. Now, the experimental flow runs in such a way that we have a compressed air line. We have a compressed air line for constant supply of air at atmospheric pressure, and then the flow meter, which has in conjunction with the air line and the methane cylinder, which provides the fuel mixture, and then which is directly supplied through a T connection, as in a T wall where the fuel and air enter at the same time to get inside the section. Now, one of them is the inlet section for the fuel and mixture, and the second one is the piezoresistive sensor, which we'll be dealing in the following slides. The primary the high-speed camera is positioned in such a way that it is at a bent angle of 45 degrees, and it can record the entire region, our area of focus, where we have a set of 4 obstacles and then followed by the bent region in the pipe. The output node is, of course, a laptop where we take out all the signals from the sensors and also from the high-speed camera. The camera was from Photon with an model Mini QX100, and it was operated between 4000 and 8000 FPS. Meaning, at 4000 FPS, the flames were much brighter. We were able to visualize the flames easily, and at 8000 FPS, the flames were darker. So we had to adjust the camera as and when it was required. And this was again controlled by BFB, the software provided by the company itself. And the lens, which was in our area of interest, was sigma 17 to 70 mm, because it could shoot at the fastest aperture available, which was f by 1.7, and this had wide range capabilities, which means the lens was able to cover the entire recordable region. The type of trigger for this camera was a manual trigger switch. We just had to click the button and then the camera started recording. Yeah. Now, the pressure sensor for setting up the initial pressures and the partial pressures inside the experimental chamber was from Keller which had a range of 0 to 10 bar, but was not precise enough. And this is why we started using the piezoresistive sensor, which had high precision of 0.02 fs and could also handle higher pressures, which meant it could run up to 0 to 200 bar, and that the explosion pressure could rather be easily measured with higher level of protection and also at a better operating range. The flow meter was from Fairclough Instruments, which was again controlled by software, CC as 30, it's the control center series 30, and this kept a track of the partial pressure from the calorific technique, which meant that the fuel and mixture was supplied in an equivalence ratio. For instance, if we wanted to test it at 0.6, 0.8, as you know, I mean, like in a series of experiments, the flow meter kept a track of the partial pressure that we wanted to achieve inside the combustion chamber. Now, getting to experimental setup part, we actually pressured in compressed air inside the pipe to ensure that it was devoid of any foreign particles or any residual CO2 if we had already performed the experiment. And then we closed the ends of the pipe with a PET plastic wall. PET is polyethylene, so polyethylene plastic walls. And we checked that delta P refers to the state where we had to check the pipe for leaks. So we had to check if the pipe was leaking, and if it was, then we had to give it out for maintenance and the further steps that ensued. Now, after this was done, we had to pass in fuel at the equivalence ratio that we discussed in the previous slide. So if we had 0.6 in mind, an equivalent partial pressure was maintained inside the explosion chamber, and we waited for an average time of 3 to 4 minutes to ensure that the pipe had an inhomogeneous distribution of the entire fuel and mixture. Now, after this waiting time, we, after making sure that everything was all set up, so we sparked the combustion chamber with an electronic conduit, and at the same time, the piezoresistive sensor was triggered through lab view, which will be again explained in the following slides, and the camera as well. So all the three were triggered simultaneously to make sure the results were recordable and also visualizable. Now, to tackle the pressure from the piezoresistive sensor, we decided that we could use a bit of process control. So this is when we started using the NR-USB 6000, which was a DAQ device, where the piezoresistive sensor had the pressure signals, which was in coupling with a piezoresistive amplifier as well. So these were in coupling, and these were sent directly into a DAQ device in LabVIEW, which meant the data could directly be the data acquisition device could function properly and then write it directly into an Excel file where we could read the pressure. The setup is again explained here. The DAQ has the voltage waveform, and then through a couple of signals from with the predefined parameters of pressure and the voltage means, it is through a merged signal and then written directly into an Excel file. Now, we also decided that we could play around and implement a better sense of process control with the flow meter, wherein we decided that we could tap in to the flow meter signal to an input node. So what we did was we created a virtual channel, and then the IOD1 control 1 tapped in the USB port to which it was connected and started getting the task channels in to the DAQ device. And the predefined parameters for air on time and off time were already set as to what time we wanted it to function and what delay it has to happen. And this function represents the timing and synchronization, which makes sure that the DAQ device has all kinds of time functions and synchronization functions in synonymous or in simultaneous workings. The trigger edge triggered directly from the task channel where it had an input at 0 or 1, which meant it could either trigger or it could stop its supply of fuel and mixture. And then the DAQ play device started collecting all the signals and started supplying the fuel and mixture inside the combustion chamber. Now this is the same for the fuel on, the previous one we discussed was for air, the one which is shown here is for fuel. So both of them were through a same pulse, which is shown here. It is again 0 or 1, it either supplies or stops. And the functions are also the same. We created a virtual channel and then the timing and synchronization followed by the acquisition of data. Now, getting into experimental results, we first had a lot of problems in visualizing the flame because the flame was, for instance, we could not really see the flame. It was not illuminating enough, so we had to use a powder, TiO2, to make sure that the flame was self-illuminating. I mean, like it could illuminate the entire section in the recorded region. And apart from that, the pipe also needed maintenance at times because it was going through a series of explosions. Yeah? Now, as we see here, this is the section between the 5th and the 8th obstacle. So if we take a time frame of 0 milliseconds, we see that after the first obstacle, it starts jumping over the obstacle and starts its propagation till it reaches 10 milliseconds, wherein we see the bent section of the pipe here, and the flame starts its propagation. After finishing over with the obstacles, it reaches the bent section. We'll come back to the slide in a minute. We can see that it enters between 10 to 15 seconds. So we see the entrance of the flame in section 2 and 3. Now, the flame has started gushing in, which means that it's directly running into the surfaces, like to the through the entire section 2 and 3. And what happens is it starts its gushing effect from 12 to 27. We see that it's starting here, and then it runs up before it hits the PET walls. A thing to be noted here is that the PET plastic walls, the polyethylene plastic walls, have an overpressure. It can sustain an overpressure of 5 bar. But in this case, with the explosion pressure that we recorded, which would be again seen in the next slide, the maximum pressure recorded was for 1.25, which meant that the PET plastic walls were just broken through with a pressure of 1.25, and excuse me, they were broken through with 1.25 pressure and with the flame propagation. Now, the flame also had a reverse flow, which meant that after hitting the PET plastic walls, it started getting back inside the section to be quenched on its own. And we can also see that in both the images over here, that over here at section 1, the flame has a vortex flow, which meant that the flame spins in and around the obstacle, which meant beneath the obstacle or around the obstacle, it starts to have a spin in motion. Now, the second case that was assumed here was for the equivalence ratio of 0.7. We can re-ascertain the fact that the propagation starts, and then once it starts hopping over the obstacles and getting into the sections. Over here we see that the bent section is between 12 to 13, and then when it starts to enter over here it starts to enter, and then the flame again has the gushing effect. So the flame again gushes in from 13 to 23. After it hits the PET walls, it reverses its flow and then quenches on its own. So this result has been provided just to re-estimate the fact that we kept seeing this effect over the series of experiments, over like around 100 or 120 experiments. Now, getting to the experimental explosion pressures. As I already said, the PET plastic walls had broken off after an impact of 1.25 bars. We see that we had recorded the explosion pressures again with piezoresistive sensors. What happened was it showed a gradual increase along with the equivalence ratios. For instance, at 0.7 equivalence ratio, it was right above the ambient pressure, so it was like 1.07, and it started gradually increasing up to the maximum equivalence at 1, so at close to 1. So at close to 1 equivalence, we observed the maximum explosion pressure of 1.25 bar. And now, we will also be getting into the flame speeds techniques, where we had to estimate the flame speeds to make sure that we had to observe the flame propagation speeds. Wherein we used the image processing technique, wherein we considered a square, an imaginary square, and then we started observing the flame propagation, for instance, from one section to the other section. If the flame had covered a distance of 2 frames, then that distance was assumed as, it was taken as 1 centimeter. And the recording happened at 8,000 FPS, which leads us to a simple math, wherein the flame speed is 8,000 into 1 divided by 2, which was 4,000 centimeters per second. So this was just a sample, for an example, to depict how we calculated the flame speed. We did this individually for each and every result that we had. Now, the average flame speeds show the same trend as we had for the explosion pressures, wherein it showed a gradual increase from 0.7 till 1, and at 1 we again had the maximum flame speeds. The plot between the flame speeds and the equivalence ratios again suggests the same, wherein at section 1 we had a maximum speed of 300 meters per second, and at section 2 and 3 we had 380 meters per second. And also, one point of interest is that the data which is shown here is not just one specific experiment. It was a weighted average wherein we performed a series of experiments to make sure we arrived at one point, and we could ascertain that this was the flame speed at this equivalence ratio. And since there was no flame front, or there was no flame shape observed, we also found the calculations a bit tough because we had to also take into effect the reverse flow of the flame and then proceed on with the calculations. So now the implications for the study. In an explosion, in the event of an explosion, we can say that before the detonation happens, there is a deflagration. This deflagration is a concept wherein there is an initial overpressure, it's an initial constant pressure around the entire constant volume vessel, and then the explosion takes place. Now, if we can have a real life example, assuming we have this room full of methane, and it's a closed system, and if there is a source of ignition present somewhere, what happens is, first, at the source, when the source of ignition strikes the fuel air mixture, the pressure remains constant over the entire vessel, and then the explosion takes place not near the source of ignition, but it happens in the weakest part. For instance, in this room, the weakest part will be the doors or the windows, and then the flame bursts through the entire room, so which means that it damages the entire household. Now, we could also develop safety models based on this to ensure that, based on this complex geometry, we could relate to the statement that at this complex geometry we had this flame propagation speed, and then we could further devise ways to have a planned safety model. Now, what the primary conclusions from our experimental setup was that the pressure, the maximum pressure decreased due to the hindrances or due to the obstacles. And now, we could also see that the flame accelerated after impinging on the obstacle, and then it started reconnecting after passing over it or passing around the obstacles. Now, the third point of interest was the vorticity formation, wherein if there was hindrances, if there was obstacles, we started seeing a spin in motion or the vortex formation of the flames, and then the reverse flow happened, which meant that at the bent section of the pipes, there is a huge influence, and the bent section influences the flame propagation speed. The future scope for the study would be on developing more complex geometries and using higher hydrocarbons to have a better contrast, for instance with propane, butane, and other hydrocarbons, and using the concept of PIV, which is particle image velocimetry, to determine the velocity vector field, so that we can have a better, for instance, a better illumination of the flame, and also have a better access to the flame fronts for calculations. And use of statistical models like PDF, like probability density functions, in computational fluid dynamics, to make sure we explore the unseen parts or the unexplored parts of the flame fronts which are not possible with the experimental study. For instance, right under the obstacle or and on the surfaces of the obstacle. So, thank you all for your patience and for your attention. I would be happy to answer questions.
Okay, let's start with the questions. So, what I missed a little bit is, can you in some way describe the effect of flame acceleration in dependence on the equivalence ratio? So you have shown these flame frames and the evolution of the flames through the steepies for three different equivalence ratios. Can you say that for which of the equivalence ratio the flame acceleration was most, and when was it least?
Yeah, so we observed the maximum flame propagation and the initial low pressures as well for a stoichiometric fuel air mixture, which meant at an equivalence of 1.0, we had seen the best of the results and the best of the explosion parameters. The fastest flame speed.
Okay. Then, when you please move back to slide 23, you have said the pressure decreases due to obstacles. So
the maximum pressure. For instance, if the
how can it happen? Because all the say similar experiments on flame propagation through obstructed geometries have shown that the pressure rises with presence of obstacles, and this is simply where the flame gets faster and the combustion is more complete, or whatever the mechanism may be.
So we also performed experiments not just with tube sockets, we have performed it without tube sockets as well, without tube sockets and also on a straight pipe. We noticed that the pressure in comparison was decreasing. So there was a small decrease in the overpressure.
For how much?
I don't remember the exact range, but I can say that it's around 0.4 or 0.5. 0.4 to 0.5.
How big was the pressure without obstacles? The maximum pressure you meant?
We noticed
Was 1.4.
1.1.
Without obstacles.
Without obstacles.
Yes, 1.4.
And with obstacles it was
1.25. We saw 1.25.
I'm quite wondering where this effect comes from, because whenever I've read about the blade propagation through abstract geometry, so the early experiments from Moen and in Norway in 1980, they indicated exactly the opposite effect. So it was also a Wednesday duct. Of course, it was much bigger than yours, 10 meters in length and 2.5 meters in diameter, and they performed a large series of experiments with different pocket ratios and so. What they could show was that the maximum pressure in the presence of obstacles is quite higher than in the absence of obstacles. So
Yes, Professor. As in
needs an explanation.
Yes, Professor. And this is why we also have our future scope of studies. We want to implement the models in a much better way and understand the effect to come to a proper conclusion that, okay, this is what happens, and this is the pressure range, and this is the flame propagation speed. We're not limited to this, this is not exhaustive. We could go further and then still check upon the models.
Maybe we should add more pressure transducers. You have mentioned in some place that the incubation pressure of the walls at the sides was 5 bar.
Yes.
Where do you know this?
Yes, we had tried, so as I told you in the first part of the experimental flow, we passed in compressed air and we started checking it as to how much it can withhold. So for instance, we passed in with, of course, with a controlling device, we got onto it to 4 bar, 5 bar, and then we saw where it broke. So at a constant airflow ratio, we saw where the PT walls broke, and then we decided, okay, 5 bar, the PT walls break.
It sounds very much for a simple foil.
But
we should check this. So I don't know what kind of material did you use for these walls. It was
it's just a polyethylene plastic.
So you went to ID, poured such a foil,
Yes.
packet and put it there. And it will never survive 5 bars.
There was a silicone also working, and it was a thickness across and was 3 layers together. So we put the silicone.
To make sure there was also no leak, so that the air was constantly distributed inside the entire vessel before it broke out. Which meant we had support.
But this was not described in the thesis.
We had
No, not so precisely. Okay, we should check it again. It's quite hard to believe that a simple polyethylene foil will survive 5 bars. Why do we use tires for our cars which aren't that thick and have a steel framing so that we can run the cars in ethylene foils? No, that was a joke.
It's not this one, the whole, it's not this one. It's the blue one.
Yeah, I understand. But it's still a belief.
What exactly is, you have a thesis here, it's on page 29.
What exactly is the structure method ratio? What's the definition you show? Page 29, is this one.
I have a
ratio between the number of moles of oxygen divided by the number of moles of fuel you need for complete combustion. This is the structure method. Okay, and then I found an interesting picture on page 24. You gave an example for a previous plane.
It's a partially new experiment, Professor. I just described.
No. Chapter 2, 1, 2, you describe what previous plane. 2, 1, 2, so page 20, sorry. Page 20, okay? So, if you can do the previous plane.
Was die Wirkung, was aber yeah, but
Again, this is the best example for a non-previous plane. If you can get a better example for a non-previous plane, you can get. Okay, funny. Now,
good. Okay, I think I have some doubts that PIV is suitable for such very fast processes. But okay, this is a different story because it wasn't part of the work. Can leave that.
okay, so I'm through with the question.
Yes, we will come back to that for the pressure, the setup of experiments when you show the pressure proof. Yes, I'm come back. No, when at the bar, yeah, this one. Yes, my question is, if the pressure transduces from 0 to 200 bars, how can you have how can you be precise with your measurement of the pressure?
yes. So the piezoresistive sensor is built in such a way that it has a quad sensor topped up with a diaphragm. For instance, the range is 0 to 200 bar, meaning that the precision was, as stated by the company, was 0.02%, which meant that the tolerance ratio was within our acceptable limits. It was the range which was provided by the company, but we could also be sure because the precision, as promised by the company, was 0 to 0.02%.
That's also a good question. So if you expect the pressure rise from 1 bar to 1.5 bar, so why do you use a pressure transducer with 200 bars? It measures only in the range of 0.5% with the measurement range, and it will be very precise.
Yes, but the absolute pressure for this, the absolute pressure range for this pressure sensor was 0 to 10 bar, and the maximum range possible was 0 to 200 bar, which meant for instance, the gauge pressure could show up to 10 bar, and the absolute pressure was also the range 0 to 10 bar. The range was, it would go up to 0 to 200 bar.
I'm making a question because I knew you say this. I want to know if you knew because it. Yeah. I don't have any.
Oh, you should have. That's in the way.
I just
like
we have many results for different rate which show the positive information between the obstacles. I'd like to know why you took these results, and I'd like to know also if you have a lot of results, why it's not like an average result. This is
yes, we did have good results in 1.0, and 1.1, but in this case I did not have sufficient images to just project it. Some of them were blurred, some of them quality of images also were a huge factor in choosing the unit set. So at 1.0, as I already stated in the explosion pressures and the explosion plane speed slide, we had good results, but at section 2 and 3 sometimes we had a blurred image or there was a broken image and we were not able to get to the exact flame from shape, so it was not worthwhile.
And how can you explain the plastic ball broke even if you have a pressure lower than 5.5 more than your plane? can handle into 5 bars.
Probably there might have been some residual foreign particles or something which we had in the previous explosions, and it was just a it was per se basis. Like we sometimes had it at 5 bar when we performed the experiments. The plastic was broke at 5 bar. Sometimes it also broke at 4.1 bar or something. It was dependent and it was varying. But the maximum it could hold was 5 bar. But I also had, we had also talks about it, saying that sometimes the plastic walls broke further, and that meant that sometimes the pipe also would have needed maintenance, and we had to give it in the workshops for having the original cell.
Gelb is wie the flame. When the flame touches the plastic wall, just melts and explodes. This is the most simple. The flame that propagates goes into the wall, when it touches the wall, going to melt the plastic. It's the most simple figure explanation we have.
Okay. Question from the audience? Question?
Ja, aber ich frage eben Deutsch.
Lesen
Deutsch?
Ja.
So meine ja. Ich habe mehrere Hinweise auf Ihre Arbeit untersucht. Erstmal bei Strom, Velocity. Da muss man die Rückstromung auch beachten. Das ist die erste Frage, weil die Velocity von Strom muss man ganz genau beurteilen. Wenn man mit dem Gas umher verbrennt muss, und die Flamme wird zurück und so schnell. Diese muss man beachten. Sie arbeiten in einem geschlossenen Raum. Ob das gut ist oder eine Raum.
Das ist nur am Anfang geschlossen.
Ja?
Das ist nur am Anfang geschlossen. Dann gehen die Folien auf und dann rollt es aus.
Der erste Bereich von der Flamme muss man gut beachten. Deswegen spielt eine große Rolle hier. Da muss man beachten und ganz genau müssen Sie die Velocity Profil darstellen. Und dann man ganz gut beurteilen, ob das die Feuerung eigen uns und das geht schnell oder geht so langsam und so weiter. Das ich meine. Danke sehr.
Could you comment on that? So also about the backward flow into the perpendicular leg of the T section.
Can you again?
The question was about in the first leg where you ignite after the flame has reached the T junction, you observe the backward flow.
So ist das.
Can you comment on the backward?
Okay.
Moment. So geht's so und so. Ja?
Kommt zurück, ja.
Ja, der Professor hat die
Okay, the reverse flow is because the system has now changed from being a closed system to an open system, and there is an influence of the external particulate matter. You cannot justify by saying this particle has influenced it. So after the flame quenches itself, like after it has stuck on the PET plastic walls, it gets back because it doesn't have sufficient sources to just move up the entire system. So it has to quench back and then moves back to section 1.
Okay.
I don't understand how the measurement works. Can you show, I think, slide 5 of the setup? Can you explain this? No, the flow diagram.
This one.
Yeah, okay.
So what happens is we have a few air mixture, I mean the air line and the methane cylinder in a gas cylinder, which is connected to a flow meter. And now we control this with Control CPC30 software. And what happens is this T section, there is a T, a small geometry like a T, sorry. So this T section helps us to have a fuel and air mixture at the same time being mixed in a proper distribution, and it passes over here. So this is passed directly in here at points D. So the D is the fuel air inlet. And at E, we have stuck in the piezoresistive sensor. And over here, we have our electrical spark igniters. And in this section, the first 4 obstacles are not our primary concern, and we start recording with the high-speed camera from the 5th to the 8th obstacle, and then with section 2 and section 3. And the camera is positioned in such a way that we're able to cover the entire setup, recordable region. And after the plastic walls are broken, we again.
Yeah, wait, why should the plastic walls break? So up to here, I've heard that gas flows in at point D, and now you're overpressuring the system until the walls break, until the ends break?
So, as in, for instance, if we wanted to perform the test on equivalence of 1.0, so we had, of course, from the equation of state, we knew from which partial pressure.
Okay, and you have a stoichiometric ratio. Okay, this is the ratio which you can change. I understand that. I don't understand how the measurement works.
Can you be specific on which measurement?
At some point, this should explode. So I assume, yeah, maybe these igniters play a role. They have to be causing a reaction at some place. And I don't understand. Are you feeding a closed system until it overpressures, and this is why these walls are coming apart, or are they being coming apart due to what's causing the flame, and where does the flame start?
Flame starts over here, and afterwards spark, and once the walls keep starting, the flame starts propagating from this section till this, and then it enters section 2 and 3. But Kristen, I'm still not able to understand that question.
Yeah, I just like to know how the experiment works.
Then yes, we spark it over here, the flame starts propagating in this section, and then over here we start recording till it gets to the till this recording section, I mean, till it breaks off the empty plastic walls. This is where we, or my
The main problem was that we couldn't find a way with little effort to purge the T-piece. So the whole section, or the whole arrangement. We couldn't find a way, so that means, in other words, it was filled, but we are not completely sure that we have a homogeneous.
So it's pretty good air initially, and then.
At first it's with air, and then it was. Did you evacuate it?
We know the concentration by partial pressure. We know how much the pressure inside, and we know how we're going to increase the pressure one time we put methane.
So there was more methane filled in than stoichiometric ratio in the flow, in the depth of T-piece. So it was a fat mixture entering and then mixing by the jet together with the air in the T-piece. But it's of course not the ideal way.
And if you fill it and then close and wait, everything should become perfectly mixed, right?
exactly. That's why we also have this waiting time. Like we wait for it to have.
Normally we would have to turn it around.
This is the first time I hear about waiting time.
Yeah, I mean,
it's pretty neat that I hear, okay, another wall sort of flooding.
No, we don't want the need.
This would be gone to the description of how the experiments work.
To have a homogeneous in the chamber,
Yeah.
you make this chamber, you mix the gas there,
Yeah.
and you make a vac inside of the pipe.
Yeah.
And you put the correct, like I know this is 0.9, and in the chamber you put this another pipe. But we cannot do this because of the plastic wall to not handle this. I wish. In fact, the valve could handle, I believe, could handle, but the chamber was the problem.
We just have the hope that as the injection is by the jet, that the jet mixes the injected gas mixture with the air. But this is not more than a hope. And then, of course, ignition, with the ignition, you need to wait until the jet has dissipated, so the momentum has dissipated. And now we have a trouble for it. Any questions? Okay, more questions?
Yes.
Yes, and here.
So you were mentioning the way you measured the pressure of the activation pressure of the band was by pressurizing the whole tube gradually until it broke off, and then measuring the pressure at that time by using this pressure transducer that you have installed, right?
Yes.
And then you got a value of 5 bars
Yes.
out of this.
Yes.
during the experiments, it was getting activated at a pressure of 1.25 bar.
Yes.
Which is not really explainable. Could it be actually because that when you measured this 5 bar, the process was quite slow, so the pressure transducer was able to record it during a long period of time, and when you have a combustion, it's a very fast process, so probably your pressure transducer is not fast enough to get that pressure before it's ventilated.
Okay, to answer your question on that, we first, as I already said, we first pressurized the entire chamber, and then the Keller sensor, the one which we used from Keller to Stretching, had helped us find out the overpressure. For this, during explosion, we used the piezo-resistive sensor to make sure, we had it in mind that this was a constant pressure. I mean, like, at that first instant, it was constant pressure, and we had placed it in such a way that it could measure it at its best precision. So, it's right at the start, so it has an even distribution and it is able to measure it. And
what is not clear to me is if it breaks enormous circumstances when you pressurize the explosion at 5 bar, why does it break during the explosion at 1 bar?
it's because of the flame propagation. The flame propagates through the obstructors and through the bent section with the speed, and flame hits it with that overpressure of 1.25, and then it will be plastic walls break.
The fire is burned. Melting. But I still don't believe in this five.
But I'd be happy to show you the experiments. I'd be happy to show you the experiments.
And
What is the
how
size
is
of
it
the
like? 50 kilograms.
when you did this activation pressure test there, so then the foils were at the left and the right, and then you started to get the cheeks, or
Yes.
and after 5 bar
It just broke. Yes.
burst.
The piezo sensor is 50 kilohertz. So it's quite precise.
And that's why it's not just accurate, it's precise. So the precision promised by the company was 0.02. If it doesn't, then we have to go to the company.
On the next slide, please go on the next slide.
Yes, sure.
One more, please. Yeah, so you were using this Red Y
Yeah.
there for methane, right?
Yes.
Yeah, for methane.
Yes.
Did you do some calibration for it? Was it actually for methane, or did you use one for air or carbon dioxide? So this one is for carbon dioxide.
Actually, yes, we have to calibrate, but honestly, it was directly stated in the manual, so we just had to follow the procedures. We had to calibrate it at first.
Can you, let's say, I put it the question differently. Can you use a flow meter which is calibrated for carbon dioxide? Can you use it for methane?
It was put up as CO2, so we had to change it. So we had to calibrate it for methane and put all the nanometers. And we can use it. We can use it. To answer your question, yes.
Can you tell me what's the principle behind it? So how can you calibrate it in a very simplest?
It's stated in the manual. I did it as per the manual. It's a long procedure. So we had to get into software, change a few of those parameters, and I don't remember precisely right now. So, it's all stated in the manual. I can forward you the manual.
Do you think you can do it with the ideal gas law just by having the density ratios? Or do you think you can do it just by using ideal gas law, having the ratio of the molecular weights?
Yes. I don't get it again. Why not?
You were saying it's a lengthy calculation and it's stated in the manual.
We did it as per the prescribed steps in the manual. I don't remember the exact steps right now. So it was a long time back. So
Good.
More questions? Questions from your side, gentlemen? No? Okay. Then we are at the end of the talk. Then we